Hi everyone, so we'll get rolling again. In this particular video, we're going to discuss uh, a quantitative perspective of acidity, and we will then expand it to basicity. And pretty much the goal, the learning objective here is by the end of this video, you would be able to use Ka or pKa to determine which is a stronger acid. If you're like doing a comparison between two acids, you'll be able to use these terms or like a quantitative terminology, and then you'll be able to predict uh, which of the two acids is a stronger acid, or like among various acids, which one's the stronger acid. Now, we will mostly use the pKa terminology or the pKa scale, not the Ka scale. Okay, but let me introduce you like this to you, and you've seen some of this in Gen Chem already. So for any acid-base reaction, and I'm just using a very general acid here. So let's say HA is an acid, and this acid is in water. You're dissolving this acid is in water. Now, in the Bronsted-Lowry definition, actually water could act as a base. Okay, we can treat that as a base. So when this acid is dissolved in water, it gives us not HA, it's going to give us A minus plus H3O plus. Or for the sake of simplicity, or to make it similar to what we've been doing, let's just say H3O plus and A minus. Okay, so our acid reacted with our base to give us a conjugate acid and conjugate base. Okay, that's the reaction that we have. Now, we can, and as we know, this reaction is at equilibrium, right? So there's going to be equilibrium. The reaction can go forward and it can go backward because the conjugate base can abstract a photon from the hydronium ion to give us HA and water. So now, even before we jump into the equation, into like some of the derivation here, which again you do not have to like, you will not be required to solve for anything, but more of an understanding. But if we look at this scheme here, this scheme, and as I've defined it, HA is an acid, okay, and it's reacting with water as a base. So if HA is a strong acid, what would it do is the question. Okay, just think about that. An acid is defined as a proton donor. It should be able to donate protons. Okay, so if HA is a strong acid, what that would mean is that it is able to donate a lot of protons. Okay, it would be able to generate a lot of protons. And a weaker acid would be one that relatively generates, less protons. So if HA is a strong acid, what that would mean is that we would generate a lot of H3O plus, and we would generate a lot of the conjugate base also, because this is donating protons. So once it donates protons, we generate H3O plus and A minus, which is the conjugate base. Okay, so that's basically what our thought process is going to be here, or that is how we would think about a strong acid versus a weak acid. Okay, strong acid should be able to generate a lot of protons quantitatively. Okay, quantitatively. So if we were to write an equilibrium constant for this equation, which we can do for like any chemical reaction here, right? So we can write an equilibrium constant. Equilibrium constant here would be concentration of products, which are the hydronium ion and the conjugate base, over concentration of the reactants, which is HA, and concentration of water. Now, like I said, we are using water as a base, but if this is an aqueous solution, right? If this is an aqueous solution, that means we're using water as a solvent also, okay? And if this solution is dilute, okay, the concentration of the acid is less, like little compared to the concentration of water. If dilute solution is, if a dilute solution is considered, then essentially this concentration of water is, it's like in excess. There's a lot of water around. Okay? So we can rearrange this equation a little bit, and what we'll do is we'll say K equilibrium times concentration of water. So I basically brought it up here. Okay, simple math there. H3O plus A minus over concentration of HA. Okay, so this new factor that we have, which is the equilibrium constant for this reaction, times the concentration of our solvent per se, the water, which was like in excess. This term here, this to combine is called Ka. That's the acidity constant or the acid constant. Okay? So this is our acidity constant, the Ka. Now, Ka, now again, if you don't think of this as a math equation, but if you try to derive like a physical significance, okay, what is this equation trying to tell me? I think what this equation is trying to tell me is that Ka is directly proportional to the concentration of H3O plus or protons that are generated in this equation, and which realize that the concentration of the hydronium ion would always be equal to the concentration of the E minus, because both the hydronium ion or both the proton and the E minus are coming from HA. So they will be generated in equal amounts always, unless there is something else secondary going on. So what this equation tells me is that the Ka is basically proportional to the hydronium ion concentration. So if we have a higher hydronium ion concentration, if this is large, then Ka is going to be large. Okay, and Ka is inversely proportional to Ha, the acid concentration. So if there's a lot of acid present at equilibrium, then Ka is going to be small. But we do not have to look at that. Okay, so I think the only physical, like the physical, the only thing that is of like physical significance for us here is that the Ka, it has a direct proportionality with the concentration of protons. So if this is large, then Ka is also going to be large. Okay. Now, Ka for acids, okay, Ka values for acids, they can range from like this can range from like 10 to the power minus 50. Okay, so 10 to the power minus 50 to like 10 to the power 10 or something. But in fact, even more. But I'm just giving you a range that is like more relevant to the kind of molecules that we will be looking at. Okay, so it can range somewhere between 10 to the power minus 50 to the 10 to the power 10. Now the question here is, so when the concentration of HA is higher, Ka would be larger, and large Ka would mean stronger acid. Small Ka would mean weak acid, or a weaker acid. Actually, it should be a weaker, because this is a relative term. So small Ka would imply a weaker acid. So the question is, of these two, okay, like the extreme ranges that we are looking at right now, which one is larger, which one is smaller? Okay, I hope everyone is saying this is smaller, that is larger. Okay, so 10 to the power 10, that would imply a strong acid. And this is where most inorganic acids have their Kas. Okay, so like HCl, that has, it's not 10 to the power 10, but it is pretty close, like 10 to the power 7 or something. Okay, but HBr, HI, they would be in this range. Okay, organic acids, which I think we haven't talked about that much, but organic acids like hydrocarbons, okay, alkanes, for example, they would have Ks in the 10 to the power minus 50, which means they're pretty much not acidic. They're like very weak acids. Okay. Now, whenever we consider this Ka scale, you're looking at all of these exponents and things like that, so it complicates things a lot actually. So we are going to simplify this a little bit. Okay. So Ka is concentration of H3 plus concentration of A minus over concentration of HA, and Ka is usually, for our purposes, in the range of 10 to the power minus 50 to 10 to the power 10. Okay? Now, to make things simpler, similar to pH, we can define a term called pKa, okay, which is the negative log of Ka. Okay? pKa is the negative log of Ka, and when you apply this math to typical Ka values, you will get pKa's. They are in the range of 50 to minus 10, so negative 10. So that is the range for like typical acids that we will be considering. Okay, between 50 and negative 10. That would be the range for pKa values. Okay. Now, when it comes to Ka, large Ka is a stronger acid. Small Ka is weaker acid. Since pKa is a negative log, when it comes to pKa, large pKa is a weaker acid, and small pKa is a stronger acid. Okay, so what I would encourage you to do is look at table 3.1 in the textbook, which actually lists pKa values for a variety of organic and inorganic acids. Again, do not have to memorize any of that, okay? But I think slowly we will develop a feel for what sort of a pK values acids have, okay? So you do not have to memorize it, but look at this table to see what sort of pK values exist. So let me give you like an example, like maybe two examples that I just want to throw out there. So HCl, hydrochloric acid, pKa is negative 7. Okay, hydrochloric acid, the pKa is negative 7, and acetic acid, which is vinegar. Okay, we used this in one of the previous lecture videos. pKa of acetic acid is 4.5 approximately. I'm just giving you an approximate number. So what does that mean? Lower pKa, negative 7, that means, or a smaller pKa means it is a stronger acid. Large pKa relatively means it is a weaker acid. Now this is not large, but it's a relative factor here. So relatively this is bigger. So that means acetic acid is a weaker pKa. Now, if you want to understand how much stronger something is, you have to actually convert it into the Ka scale. Okay? So for example, what I can tell you is that HBr, its pKa is like -9 or something. Okay, and what that means is HBr has a lower pKa compared to HCl. So HBr is a stronger acid than HCl also. Now, how much stronger? We would have to convert these into Kas. So when we talk about Ka, we're talking about 10 to the power 7. That would be the Ka. And we're talking about 10 to the power 9. And so now we can see the magnitude of difference. So HBr is about 100 times more stronger acid than HCl. Okay, so that is the discussion on pKa's and Ka's. Now, once we understand pKa or Ka, now we can apply this to acid-base equations and predict the direction in which they are favored. And we can also apply this to understand basicity. Okay? So any acid, when it reacts with a base, it's going to give you a conjugate acid and a conjugate base. So based on pKa, okay, pKa helps us predict acid strength, which we will call as acidity. Okay. So if an acid, let's say, is strong, okay, if HA is a strong acid, then its conjugate base, okay, then its conjugate base, which is A minus, this is usually, not usually, this is a weak base then. Okay, so we can also use pKa's to predict which is a stronger acid and which is a weaker acid. Which is a stronger base and which is a weaker base. Okay, so that is also possible here. So let's again apply this to HCl and acetic acid maybe. So HCl, you know, pKa, we just looked at was -7. Acetic acid, I'm probably drawing the molecule in different representations. Okay, maybe a mix. So let's keep track of all of it. So that's 4.5. If I draw their conjugate bases, okay, this is an acid. If I draw their conjugate base is obtained by the loss of a proton. So when HCl loses a proton, we will get Cl minus as the conjugate base. When acetic acid loses the proton, we will get what's called an acetate ion as the conjugate base. So this is a stronger acid, this is a weaker acid. Okay, stronger acid, weaker acid. Okay, because this is a stronger acid relative to acetic acid, its conjugate base should be a weaker base, and since this is a weaker acid relative to HCl, its conjugate base should be a stronger base. Okay, so we can use pKa values to also get some sense about basicity of organic molecules. That is the point that I'm trying to put across here. Okay, so we're going to stop right there, and in the subsequent video, in the next video, we will use pKa values to predict the direction, the favored direction in acid-base reactions. Okay, like is a reaction favored in the forward direction or is it favored in the back